Okay. Okay, great. So welcome everyone. Today we are going to have Adrienne giving a presentation. And so Adrienne Tuynman is a second-year PhD student in the INRIA school team based in Lille, in France, where she works with Émilie Kaufmann and Rémi Desjeunes. And before that, she completed her master's degree at École Normale Supérieure Paris-Saclay in the MVA program. And she's interested in like multi-armed bandits, reinforcement learning, but more specifically like identification problems, which I think is what she's going to talk about today. So Adrienne, thank you for presenting, and can start.
Well, thank you very much for having me. I'm very glad to be here, and I'm very excited today to be talking about my work. And so I hope that by the end of this presentation, you'll be just as excited about this as I am. So indeed, I'm going to talk about best policy identification in average reward Markov decision processes without prior knowledge. So first, of course, we'll introduce a few of the things that we'll be studying here. And then we'll look at various measures of complexity for this problem, and we'll be comparing them in various settings before, of course, suggesting solutions to all the problems we'll be encountering. So first of all, average reward reinforcement learning. So what exactly is it, and why do we care about it? So here we're looking at finite tabular MDPs. And so we have a set of states, a finite set of states, finite set of actions. So throughout this presentation, whenever I present an MDP, I'll be able to draw it. So with each arrow depicting a certain action, going from one state to another. And I'll also be showing the reward that the agent gets when it takes this action, and the transition probability that in that state taking that action will end in that other state. And so in the end, our MDP, it's defined by its set of states and actions, but also by a bunch of stuff that we don't really know. So the transition probabilities, what is the probability when we are in a given state with a given action to go to another state? And also the reward that we would get when we are in state and we take an action. And here we are especially focusing on deterministic policies. So anything that takes a state and returns one action. And so what we want to do is to find a good policy. And so a good policy, yes, but with regards to what? And so in RL, there are different objectives that we can want to maximize. You can want to maximize the finite horizon rewards. So you just care about the rewards that you'll get up to a certain time step, and then you don't care what happens afterwards. You can look at the discounted setting, in which each subsequent reward matters just a bit less than the one before it. But there are some settings in which there is no natural definition of the horizon, and there is no natural definition for discount. If you want something that will work all the time, forever, asymptotically, or you just don't really know up to which point you want it to work, that's when you care about the average reward setting. And so in this setting, you want to maximize the Cicero mean of the rewards. So you want to maximize the reward that you'll get in average up to infinity. And so it's quite interesting when you don't have natural definitions for the horizon or the discount, because you don't need to tune them, you don't need to invent them out of nowhere if you don't have them. But the problem with this setting is it can be very finicky. It can be very, very sensitive to small details in the MDP. For example, imagine you had a certain state that was a trap state, and it's very, very bad, but you don't have that many chances of landing in it. There's a very, very small probability of going there if you're in a given state and do a certain action. Well, in the finite horizon setting, you don't really care that much about that bad trap state, because odds are you're not going to land in it up to your certain horizon. So it's fine. If you're looking at a discounted setting, well, maybe you'll land in it in 1,000, a million time steps. But it doesn't really matter again, because by that time, the discount factor will just be so tiny that it doesn't really matter. However, in the average reward setting, well, if you ever go into that trap state, then you're stuck in it, and you always get very bad rewards. So in the average reward setting, you really need to avoid that trap state at all costs. And so you need to really have explored your MDP to find out what you must not do. Which means that this setting can be a bit more dangerous, a bit more difficult. So then all this setting, it's governed by a few equations. So if you're familiar with the finite horizon or discounted settings, then you're used to the Bellman equations. And in the average reward setting, we call them Poisson equations. They're kind of the same. And so if you take P of pi, the transition matrix for a certain policy, you can define its asymptotic version. So when you look at the Cesaro mean of the powers of that matrix. And with that, you can say that the gain, so the thing we want to maximize, the Cesaro mean of the rewards, that's going to be that asymptotic distribution matrix times the mean reward vector. And beyond that, you can also define the bias. And so the bias, it's kind of the value function in the other settings, but not really. The bias vector, it's something that will basically quantify how happy you are to be in a state compared to the others. So it's a vector of size S, and it's defined by the difference between the immediate reward and the asymptotic reward. And so if there's one state, for example, that is very, very close to very high rewards, then its bias will be way bigger compared to states where the immediate reward is quite low. And so it's those two objects, the gain and the bias, which satisfy the Poisson equation, and especially the optimal Poisson equation for the optimal policy. And so, great, now we have this equation that puts a bit of order in our setting. And now, remember, what we want to do is find algorithms that find a good policy, so a policy that maximizes the average rewards. And so what that means is we want an algorithm. So it's something that will iteratively pick a state, an action, observe, and do that over and over again until it meets a stopping condition. So to look at it a bit closer, there are two models that you can look at. Either you are in the generative setting, in which case your algorithm can simply sample anywhere it wants to. So if there's a state that's very hard to reach, it can just choose to sample in that state. It doesn't need to go over there. So in the generative setting, you choose your state, and then you choose the action you want to perform in that state, and you observe what happens. So what is the next observed state, and what is the reward that we incur? And by doing that over and over and over again, we gather more and more information until the algorithm says, okay, I'm done, I stop. It meets a certain stopping condition, and it returns a policy that it thinks is good. In the online setting, it's almost the same. Simply, you don't allow your agent to sample just from any state. If it wants to sample from a given state, it has to arrive there. So then in the online setting, your agent can only select the action that it wants to perform, and then whatever state it ends up in, that's where it will start in the next time step. And so that's our algorithms. That's what we want to craft. And we want to find algorithms that are correct and that are fast. So by correct, we say that the policies that they return must be within epsilon of the best possible gain, which we obviously don't know, with probability bigger than 1 minus delta. And so this is what we call epsilon delta back algorithms. And so we're only interested in those algorithms, that with high probability return good enough policies. And of course, if you had infinite observations, then you could do this quite easily. So we want to minimize tau. We want to minimize the number of time steps required before the algorithm says, okay, I'm done. Here is your result. And now, of course, for different MDPs, it's not going to take the same amount of time. If you have very simple MDPs, then maybe you need very, very few samples. If you have very complex MDPs, then you might need a lot more. And so then, how do you minimize tau if it depends on the MDP? Well, one way is to find ways to quantify the complexity of an MDP. And so, obviously, like the state space is going to quantify the complexity of the MDP. If it has a lot of states, then it will be harder to find the best policy. If it has a lot of actions, it will also be harder. But those aren't the only things that matter. And so in prior literature, in the best policy identification problem, but also in other problems in theoretical reinforcement learning, there are 3 different measures of complexity that seem relevant here. So the first of them is the diameter, which we call d. And heuristically, it's the time that you would need to go from one state to the other. So if there's, for example, one state that's very, very hard to reach, it means you'll have a very high diameter. However, if, for example, in each state, you can take one specific action that leads you to any other state, then you might have a diameter of just 1. And this MDP is indeed easier to learn because you could always just go anywhere and instantly go where the high rewards are. And so that's why the diameter is heuristically a good measure of complexity. There's another that's the mixing time, which we won't really focus on, but it's still important enough in the literature to bring up. And so the mixing time is the time necessary for the distribution of the states to be close enough to the asymptotic distribution. So as you progress through time, the distribution, the states that your agent will be is a probability distribution, and it will at some point converge towards the asymptotic one. And if you converge very, very quickly, then it means that very, very quickly you will observe asymptotic behavior. And so to find the average reward, well, you're quite happy. You're already observing the behavior that you want to maximize. And if it takes a very, very long time to converge, then it might be a bit harder to derive the asymptotic behavior from your empirical finite time one. And finally, another complexity measure that's very important in our work and in prior literature is the optimal bias span, which we call H. And so remember the bias, it was a vector that measured how happy we are to be in a state compared to the other. Well, if there are some states in which you are very, very happy and some states in which you are very, very sad, it's actually a bit harder to find the best policy. Whereas if everyone is equally happy, if all the immediate rewards are kind of the same, then you can't really mess up a whole lot. Because if you mess up, well, you're still in a high reward state, so you're not actually that sad, so you can still be very optimal. And so that's the optimal bias span, just the span, so maximum value minimum minus minimum value of the optimal bias, so the bias of the optimal policy. And so with those 3 complexity measures, we kind of want to ask, well, which one is the best? Which one most accurately conveys the complexity of an MDP? And if you look at the literature, you might think that the problem is already done. Because there exists a paper that shows that there exists a specific MDP where any kind of algorithm needs at least SAH over epsilon squared logarithm of 1 over delta time steps. So whatever algorithm you want, it can be as sophisticated as you want, you will need to pay this SAH over epsilon squared. And there's also an algorithm that for any kind of MDP, no matter how complex it is or how weird it is, will give you the right answer within SAH over epsilon squared samples. And so we have a lower bound, we have an upper bound, and both of those match. So are we done here? Well, actually, all of those papers assume prior knowledge of H. So it's a parameter in the algorithms that are used. And so the first thing that we'll ask ourselves is that a practical assumption? Can those algorithms still be used even if I myself don't know the H of my algorithm? And so that's what we're looking at in the first place. So if I assume, can I try to indeed estimate this H and plug it into my algorithm? Can I try to do that? If I want to apply my algorithms, that's what I need to do. However, our first discovery in our paper is that it's really not possible, not feasible to estimate H. And so for this, there's this simple example, simple illustration. So if you give yourself an MDP with 3 different states, 1, 2, 3, and 2 different actions, so a full line action and a dashed line action. And your objective is to find the best possible policy. And there are 2 quantities that are completely unknown. There's a probability P, which is the probability to go from state 3 to state 2 when you perform the dashed line action. And there's also the quantity R, which is the mean reward when you are in state 2 and perform the dashed line action. So those 2 are unknown. And what happens is, if you take R to be slightly smaller than 1/2, then to get the best possible policy, you want to go to state 1, where you have your 1/2 reward. And so your optimal policy is going to be the full line one. And in that case, if you take the full line policy to get to state 1, well, if you're in state 2 or 3, you're not really that sad, because you just need to take 1 step and you are in your high reward state, which means that the optimal bias band is very small. Actually, it's only 1/2. And so that's only if R is a bit smaller than 1/2. However, if R were to be just a bit bigger than 1/2, then to get your best policy, you would need to go to state 2 to get that R reward. And so you would need to take always the dashed line action that is the only one leading you to state 2. But if you are in state 3, for example, you are actually very, very sad. Because if you are in state 3 and you take the dashed line action, there's only a small probability that it will lead you back to the high rewards state. And so you will need a lot of samples to go from your 0 reward state to your high reward state, which means that the bias band is going to be very, very big, because you're way sadder to be in state 3 compared to state 2. And so here we have 2 MDPs. The only difference is the value of R. And so those 2 MDPs can be very, very close. So you would need a lot of samples to hopefully distinguish them. However, their biases and their optimal bias bands are very, very different. And so then how can you estimate your value of H if such a tiny discrepancy that's so hard to see can lead to such huge differences in what you're trying to estimate? And so it's with this idea that we have the following results, that for any probability in any time horizon and also any tightness, there exists some ergodic MDP with relatively small h, so h of 1/2, such that any algorithm that computes an upper bound of h within the given tightness with high probability will need more than t samples, which means that even if you bound the possible h that you actually have, you cannot estimate it within finite time. You cannot bound the time necessary for it. And so then all the algorithms that assume knowledge of H, I completely cannot apply them if I do not have that prior knowledge, because I can't estimate the thing that is a parameter of the algorithms. However, there might be something that we can do even if we know nothing. Maybe we don't actually need to estimate H, because if we dig a little bit deeper, if we really look closely at the lower bound we had, that was in SAH over epsilon squared, then actually the lower bound is in the diameter. It's in SAD over epsilon squared. And the only thing that you need to put on top of this is that the diameter is bigger than the optimal bias span. So your lower bound in D is effectively a lower bound in H. But what if the more accurate lower bound is the one in the diameter? What if the diameter were a better way to quantify the complexity of an MDP? Maybe we could try to reach this initial lower bound. And so that's what we're going to do, at least firstly in the generative model. So in the generative model, remember that we assume that we can just move anywhere we want, as we want. We can sample from anywhere. We're not really bound by the state we end up in. And we're going to try to use the diameter instead of the optimal bias span. Because one very good thing about the diameter is that we can estimate it. So there exist methods to estimate the diameter within constant factor. So you can compute an upper bound of the diameter that is at most off by a factor 2. And you can do that while bounding the sample complexity for it, of course. And on top of that, all the algorithms that required prior knowledge of H actually just require knowledge of an upper bound of H. And the diameter is an upper bound of H. And so now we have all of our building blocks. And so if we put them together, fine-tuning the parameters well enough that it fits together, we get our algorithm, which is the diameter-free exploration algorithm. So in which you estimate the diameter and then plug that into the best policy identification procedure. And with that, you get an algorithm that is epsilon delta pack, which means that it's good enough with high probability. And when you look at the sample complexity, you might think, oh, there's a bunch of terms that I don't really know where they come from. This doesn't look very good. And you might be right, except in the small epsilon regime. If you look at the small epsilon regime, then the only term that remains, the dominating term, is going to be SAD over epsilon squared times the logarithm of 1 over L delta, which is actually the lower bound. And so here we have an algorithm that is basically just smushing blocks together, which is optimal in the regime of small epsilon, which is already something, and this algorithm is doable without requiring prior knowledge of H. And so now that was all in the generative setting, which is a bit easier because you can just move anywhere you want to take your samples. However, one thing that might still be possible in the generative setting is to find some other way of taking samples, some completely different algorithms that might still match the lower bound in H. So we can't estimate H, and we can't maybe use the previously existing algorithms, but there might be another way to reach a lower bound in H. However, in the online setting, where you have to go look for your samples without teleporting throughout your MDP, it's actually not really the case. And so in the online setting, your optimal bias span, H, is most definitely not the right parameter. To convince you of it, here's an MDP with a bunch of states. There's one state, state S1, in which with high probability, you'll just loop with a reward of 1. And so it's a good state. However, with a small probability p, it will lead you to S2, which is a trap state. When you arrive in state S2, your only solution is to take a very precise sequence of actions, J1, J2, etc., up to JS-1, to get back to S1. All the time you get no rewards at all. And if you do just one mistake, then you go back to state S2 to try the sequence again with no rewards. And so here, in the generative setting, well, it's not that hard. You just have to look at all the states to find the good actions to take. But in the online setting, well, when you start in S1, you have to do a lot of steps to hopefully land at some point in S2 to learn the right sequence. And if you don't get to S2, then you don't learn the right sequence. And then you cannot be optimal, because you'll be stuck forever in 0 reward states. So any optimal algorithms will need to go to S2 and will need to pay that huge costs to go to S2. And so as P grows small, then the necessary sample complexity will grow very, very big, inversely proportionately to P. Now let's look at our diameter and optimal bias span. The diameter is very big, because if you take 2 states, S1 and S2, the time necessary to go from the first one to the second one is very, very big. So your diameter is inversely proportional to P again. However, for the optimal bias span, if you are in S2 and you're using the optimal policy, are you that sad to be in S2? Well, you're not really that sad, because you are using the optimal policy. You know how to get out. The only thing you need to pay is S steps to get back to state S1. And so in this setting, the number of samples necessary will be exponential in H. And so in the online setting, H is definitely not the right parameter, because at some point you do need to explore everywhere. You do need to pay the diameter, which can, as shown by this example, be way bigger than H. So then we're in the online setting. We think we would probably need to pay the diameter. What do we do now? Well, we can just use the diameter again.
Right, so just before you move on to the next result, quick question, or quick clarification.
Yes?
So I guess in this case, you cannot hope to get a guarantee depending on H, but so if we look at the regret, I think you could get it without the knowledge of H, which I think is what Victor would talk about. And so
yes.
But so could you maybe clarify why, for instance, we cannot convert the regret guarantee into a pack one and this kind of thing?
The problem of converting regret warranties to best policy identification ones is, yeah, because I do think, so is that for next week that it's possible to have regret scaling in H even without knowing H at all?
Yes.
Yes. We've looked at that and it's not possible, because the regrets that you're looking at, it's still the regret up to time t. And so your regret up to time t, it's not going to give guarantees for asymptotic behavior. And so in regrets, basically, asymptotically, you'll be able to learn the right things to do. But in best policy identification, you can't really take what your algorithm would have learned at time t and find out what it would have done asymptotically. And so that's why it's not really possible to transform regret things. Yeah.
So is it because the difference between the regret and the pseudo regret depends on the mixing time? And so
yes, it's definitely a mixing time problem.
So the conversion would work for the pseudo regret, but not the regret. Okay.
And yeah, at some point we wondered, and we're still wondering, it would be interesting to look if you could, with knowledge of the mixing time, maybe use regret algorithms. So that would be another problem, and it's definitely not as simple as in other settings where you can just take good regret algorithms and say, if we're good with the regret, we must have been doing something right, and then just samples the policy. That doesn't work here.
Okay, I see. Thank you.
Thank you for your question. And yeah, so as I was saying, H is definitely here not the right parameter. But so we could just use the diameter again. What did I say? Optimal bias band is not the right parameter. We can just use the diameter again, because the diameter, we can estimate it in the generative setting, but we can also just estimate it in the online setting as well. There are algorithms that do that. And so once you have estimated your diameter, then you can take your best policy identification algorithm, and you can mix it with the ghost PRL algorithm. So ghost PRL is an algorithm to which you give a bunch of states that you want to visit, a bunch of samples that you want to collect, and it will go to those states. So it's another brick that basically converts generative algorithms into online algorithms. And so with this additional brick that you add into the system, you can get online DFE. So you estimate the diameter with online procedures, and then the best policy identification algorithm says which samples it wants to gather, and ghost PRL goes to get them, and in the end, you have your good policy. And so here, the sample complexity of online DFE is computed, and you notice that there's an additional D factor in the sample complexity, which is basically the what is added by the ghost PRL procedure. Because if you want to just go collect samples everywhere, you need to pay that diameter to travel throughout the MDP. And that's where it's come from. We don't yet know if that added D factor is necessary, but it's there so far. And so now, all those algorithms, they're kind of just made up of a bunch of blocks. So we estimate the diameter, and then we plug it into other stuff. And if you look very closely at what happens in the other stuff, the best policy identification algorithms that exist prior are basically returning to the discounted setting. Because what happens is the average reward setting is basically the discounted setting with a very, very high discount. As your discount goes to 1, the behavior of your rewards is going to converge towards the average rewards behavior. And you just need to find the right discount after which behavior of the policies is going to be the same. And so if you know H, or an upper bound of H in any case, then it is known that taking for discount 1 minus epsilon over 12H, or epsilon over H with some constant, if you take any discount above that, and you find epsilon optimal policies in that discounted setting, they are still going to be epsilon optimal in your average reward setting. And so then you can use the optimal algorithms in discounted MDPs. And so what is used nowadays is uniform sampling, which means that the algorithms in this field are a bunch of bricks. And then within those bricks, we go back to the discounted setting and we do uniform sampling. And that's not really usually how online algorithms are built. Usually it's more about sampling and stopping rules. So instead of building a bunch of bricks, we say, okay, how do I want to sample? What would give me information? What would lead me to conclude faster? And you sample like that, and you check a stopping rule that says, okay, I know enough. And so what's interested us is how can we develop a stopping rule that says, okay, you've learned enough, so that then people could focus on finding good sampling rule, good ways to explore the MDP to meet the stopping rule as fast as possible. And so that's what we're doing more moving forward. And what we did was taking inspiration from value iteration. And so value iteration, it's when you know your transition matrix, you know all the probabilities, you know all the rewards, you know everything, and you want to find the optimal policy. What you can do is you define an operator, the operator L, which is basically the right-hand term of the Poisson equation, the optimal Poisson equation. And you just iterate it a bunch of times. And if you iterate it a bunch of times, you still need to know when to stop. And so you have the following results found in the Tuynman, which is that when the span of LV minus V is smaller than epsilon, then the gain of the induced policy is within epsilon of the optimal gain. And so all you need to do to find your optimal policy and also its gain is to iterate this L operator over V, which is basically an estimate of the bias, over and over again until its span is small, until LV minus V is small. And so that's for value iteration when you know everything. But so we can't know everything, but we can still estimate it. And so what if we built estimators for PSA times V? What if we built estimators for the L operator? What if we built estimators for the span of LV minus V? Well, if we build those estimators well, then we could use the stopping rule. And that's precisely what we're doing. And so here, what this theorem says is if we do build all of our estimators, then we're going to find the gain. And so for some vector, which is Bn, so it looks like a bias vector, but it might be just any real vector over S. If we have a confidence interval Lu for PSA times B, and you also define the quantities I sharp and I flat, which are upper bounds of R plus PSA B minus B, upper and lower bound, sorry, of the reward plus PSA B minus B. Well, then your I sharp is an upper bound with some probability of your LV minus V, and your I flat is a lower bound of it. And so because you have your upper and lower bounds, then by the theorem that we had just before, we can bound the gain of the induced policy within those two. And so if with those estimators, you effectively have an upper bound of the suboptimality of your policy. And so with that, we can craft a stopping rule. And so if you take U and L, chosen such that LU is a confidence interval with probability 1 minus delta, then you can define the stopping rule that the span basically of the i's is smaller than epsilon. So remember, I sharp is an upper bound of LV minus V. I flat is a lower bound of LV minus V, which means that the max of the I sharps minus the min of the I flats is going to be an upper bound on the span. And as we said, when the span of LV minus V is smaller than epsilon, then we have found an epsilon optimal policy. And so here, once this upper bound of the span is smaller than epsilon, we have found an epsilon optimal policy. Except if the PSA times B weren't in the confidence interval in the first place. So that's just the error event. Which leads us to our theorem that for any kind of sampling rule you might have, for any kind of sequence of bias vectors B, If you just stop whenever this stopping rule is met and you recommend the induced policy, then you are epsilon delta back. And so now the only question is to find a good enough sampling rule to not just take random samples that might not be relevant. And so now one might just wonder, is this all completely tractable? Can I just define those confidence intervals? Can I do all this? Is it feasible? There are some choices you can actually take. So for your confidence regions, you can define Kullback-Leibler divergence-based confidence regions, where will give you tractable, computable confidence intervals, so those exist. And as for the sequence of bias vectors Bn, well, in value iteration, they're just empirical versions of the bias vector that you have so far. And so you could want to just try to use the empirical biases, so the bias of the empirical MDP you have so far. But you can do a bunch of other choices. And so, for example, you can try to be greedy with regard to the stopping rule. You just try to see, is there a certain bias vector that would put my stopping rule, that would verify my stopping rule. And so there are a bunch of different choices, but those are possible. So this stopping rule is actually possible to implement. Now, for the analysis on the sample complexity of it, we have some preliminary results about the sample complexity of this kind of stopping rule compared to paired with uniform sampling. So it's not the best sampling rule there is, but it works. And the point here is to look at what ingredients might be necessary for this analysis with maybe smarter sampling rules. And so you can rewrite the Poisson equations, which are, as you recall, the equivalent in our setting of the Bellman equations. You can rewrite them as just a linear operation. It's just some matrix pi times basically the bias vector up to certain few changes. And that product must be equal to the rewards vector. And so once you've rewritten your Poisson equations like that, you can define a few quantities. So small delta 1, which is the difference between the best possible gain and the second best possible gain. Big delta 1, which is the maximum of the norm of the inverse matrix pi. And you can define big delta 2, which is the maximum infinite norm of this small h vector. And so those are all quantities that we're not really that used to dealing with. It's not the diameter, it's not h. We don't yet know precisely the links between all of our tools. But those are the quantities that appear when we compute the sample complexity. And so we get some sample complexity where we see SAH over epsilon squared. So we try to be happy, but then we see that there's all those other quantities that just might be very, very big and that we don't actually know how to estimate yet. And so something that I would be interested in is looking at how those quantities compare to previously existing complexities. So how do they compare to the diameter, to the mixing time, etc. To hopefully understand this analysis better. But of course, maybe we don't even need those parameters if we do smarter sampling rules. This is just generative setting, uniform sampling. And so to understand where they're coming from, they come from a simulation lemma. Because what really matters actually here is how fast will our empirical biases converge towards the actual one. And so, because if they converge very, very quickly, then it will be way easier to estimate those PSA times B quantities. And for that, the simulation lemma makes those quantities appear. That's where they come from. And that's so far the limiting factor in our analysis. And so in the end, we do have a stopping rule. It just needs to be paired with smarter sampling rules. and analysis that are derived on this, where we hopefully understand all those new quantities a bit better. So now let's look at everything that we've learned in this last 50 minutes and conclude a bit. So we've seen that it's impossible to estimate age. So if we don't already know it, we can't estimate it and then plug it into previously existing algorithms. However, we've seen that it's possible to estimate the diameter and to harness that estimation to get optimal algorithms in the regime of small epsilon with a generative model. We've seen that it's completely impossible to have algorithms with simple complexity polynomial in age in the online model, whether we try to estimate it or not. It's really not the right quantity. And finally, we've shown that there is some stopping rule that is correct without any prior knowledge. And that's just one thing for a good sampling rule to be paired with to create good algorithms that don't require so many building blocks. And so a few perspectives that I'm excited about is looking at better sampling rules outside of just uniform sampling. So what if we try to maximize the information we get? What if we try to meet the stopping rule as fast as possible? Are there better ways to find those samples and to analyze, of course, those sampling rules with the stopping rule to get good sample complexities? Also, another thing that would be interesting to see is, so far we just assumed that we had nothing about age, about D, we know nothing. But we could try to only look at simple enough problems and say, okay, the very, very difficult ones, it's fine, I'm not going to get them, it's okay. And so, for example, the very problematic settings is when you have very small but non-zero probabilities, when there's a state that's just very, very, very hard to reach. That's what we saw in the online setting. There's this MDP with just the state S2 that you're not going to see that often. But maybe we could just say, okay, if a transition probability is not zero, it must be bigger than some predefined quantity. So that's something we could look at. Could we maybe, with that additional knowledge that is maybe more natural than knowing age, could we derive more knowledge? Could we derive smarter algorithms with that? And finally, something that I'm starting to look into is, so far we've looked at gain optimality. So we're trying to optimize the gain in the long run. We're trying to optimize the reward in the long run. But maybe there are two policies that are gain optimal, that will give me great wealth in 1,000 years. But maybe I also want to have my good rewards right now. And all my policies that are optimal in the long run might not be optimal in the short run. And that's what we call bias optimality, wanting policies that are not only optimal asymptotically, but also right now. We want those that have the best bias possible. And so a question would be, can we leverage the methods of gain optimality into bias optimality? Is there an equivalent of the optimal bias span, but for bias optimality? Can we do anything like that? Can we find maybe the discount factor that's big enough that the behaviors of the policies are similar? How do we even define near optimality, near bias optimality? And there's also, if you want to go further, there's gain, there's bias, but you can also define a whole slew of other optimality criteria up to Blackwell optimality, which is, if you're Blackwell optimal, you're everything optimal. And it would also be interesting to look at how we can leverage average reward optimality for Blackwell optimality. So thank you very much for your attention. I hope that you are convinced also with me that this is a very interesting topic with a lot of interesting perspectives. And so if you have any questions or suggestions, I'm happy to listen to them. Yes.
Yeah, thank you for the very clear presentation. It was very enjoyable. Wait, so on the future directions, you said you would look at a case where the complexity is capped by making like a reachability assumption.
Mm-hmm.
I mean, or at least what I refer to by reachability is like this lower bound on the probability of ending up with some state action pair.
Yes.
Yeah, I guess that's a reasonable assumption to make, but like, is it reasonable to assume that you would have access to this quantity, which could be like, I don't know.
I mean, it really depends on the setting. I guess in the practical sense, maybe not, but maybe you also want to say, well, I do want to be epsilon optimal, but I don't have infinite time in my learning. So I might just say, if the MDP is really that complex that I would need 3,000 years of training, then maybe that's fine, and I don't really care about those fringe cases. So it's not necessarily an assumption that you make about the MDP. It's just that if it's not actually respected, I don't really care. It's fine.
Yeah, okay. Yeah, okay. I see.
So related to that, if you're saying I don't care what happens in sort of 3,000 years or so, is that almost like imposing some sort of horizon back into the problem? Is there some connection?
I don't think so, because you're not putting a horizon on when do the rewards not matter anymore. Mm-hmm. You're just saying, I don't want my training time to be that big. But I don't actually know how those two relate. Like, obviously, if your MDP is really that complex with very hard to reach states, I don't quite know. But yeah, they're not exactly the same things, no. Capping the training time and capping the horizon of relevancy of the rewards.
Of course, yeah. Yeah, I guess capping the training time is more like changing the value of epsilon you're aiming for.
Maybe, yeah.
No? Okay, maybe I've got completely wrong end of the stick.
Yes.
Sorry, thanks for the presentation, for a nice presentation. I also had a question about, okay, for example, when we know that the diameter is an upper bound for the optimal bias, and then we say, for example, in some environments, in some MDPs, the number of times that I need to have a, for example, packed result is exponential in H, but it's polynomial in D. Does that mean that, for example, this upper bound is a very loose upper bound? And does that overall mean that, for example, if you have a regret bound based on D, then it's the very loose upper bound? Because you might have, for example, upper bound based on H, but it's exponential. But then you can, for example, just put this exponential dependency on H as something like, for example, D. Is that true, or?
Well, the problem in the online setting is that the diameter can be really, really big, even with small h. And I think it's been shown that the diameter can actually be arbitrarily bigger than h. If you have a state that's very, very hard to reach, you could have a huge diameter and a small h. So that means that, yeah, if you have an upper bound in the diameter, there are some MDPs in which you might not be optimal at all, regret-wise, because H is just so much better if you can reach it.
I see. So, but because what I got, it was something like, for example, when we have an upper bound over D, or when we estimate D, this can be upper bound, can be an estimate for the upper bound over H.
Yes, so, but the problem that we have in the impossibility to estimate H is that it's impossible to estimate H with given tightness. And so if you want to be tight, that's not possible. You can just provide D, but then it's just not tight. That's the problem you have.
I see. Okay, thank you.
Thank you.
Yes, Victor.
Yeah, I have a question. Can you hear me correctly?
Yes.
Okay, so we know that you cannot have pack guarantees within the rating of the bias span without prior knowledge of the bias span. You know, we can have something with a diameter. So is there something in between? For instance, what about the mixing time?
We haven't looked at the mixing time enough. One thing that's maybe important to note is in the online model, we can't do age, that's fine. But in the generative setting, it might still be possible to match the age lower bound, just not with the methods that we have currently. Now, if I remember correctly, the mixing time is an upper bound of age, but I don't remember how it relates to the diameter.
It's orthogonal, like it can be arbitrarily small, arbitrarily big, whatever. It's not related to the diameter.
Okay, yeah. So then it might not be also the best idea if it's not related. Yeah, I don't know of any other complexity measures that might be in between. Sorry.
Okay. No, sure. Thank you.
Thank you.
I think there was some example that you were looking at, or I think it was maybe a lower bound from another paper where you said H was equal to D.
Mm-hmm.
Do you know any more details about what exactly in the problem makes these two things equal, or is it better if I just look it up?
It's just the MDPs that's like this. Since it's a worst case bound, it's just a given MDP in which you would need that many samples. And it just happens that this specific example has similar H and D. I couldn't tell you how exactly the MDP is built.
But it's like a property of it's the structure of the MDP that that they've chosen such that this has.
Yes, I think it's, if I recall correctly, it's quite deterministic MDP, which is basically shaped like a big tree, which makes those two quantities very close. But yeah, it's really specific to that problem.
Maybe I should stop the recording.